Hey there, in this video we are going to look at the stereochemical configurations of the monosaccharides, and we are going to start with the simplest of the sugars, and that is glyceraldehyde. Now we can be able to draw this compound using the normal kind of conformation in the 3D, or we can draw it in terms of Fischer projection. And in the Fischer projection, the way we do it is we use the vertical lines, or we could use the horizontal lines. So I want you to look at it this way. The vertical lines are the ones that actually, the ones that are going into the screen, so like they're projecting away from you. So then we show them using these dashes. And then the horizontal line, when you look at it, you should be able to visualize it as if they are projecting towards you. So they are kind of facing the direction where you are. They're coming out of the screen towards the direction where you are. So by taking a look at the glucose, we can be able to visualize it in such a way that the horizontal lines we make them bold so that you should be able to see them as if they're coming towards you. We can use this strategy to determine the R and the S configurations. So let us take, for example, if we label the compound, let's say this is carbon 1, 2, 3, 4, 5, and 6, then we can be able to determine the stereochemistry at position 2. Let us zoom it so we can be able to see it clearly. Then we have also carbon 3 connected to another carbon and the other ones. So then we have the one labeled 1, carbon number 2, carbon number 3. Now our interest is to label carbon number 2 as either R or S. To do that, we are going to employ the concept that we have learned before, and that is the Kern-Ingold rules, where we are going to prioritize the substituents in the order of the atomic number. So starting from the stereo center 2, we're going to have OH being priority number 1 because oxygen is of a higher atomic weight than the carbon here, and this carbon here. Here we only have hydrogen. So priority number 2 is the carbon connected to the oxygen double bond, that's the carbonyl. And then priority number 3 is the carbon connected to another carbon and oxygen, which means we are going from, moving from 1 to 3, it's going to be counterclockwise configuration, which is an S. However, when you look at it carefully, we can see that the lowest priority, which is priority number 4, is actually up. So it's facing towards our direction. So that means we need to flip this molecule so that the lowest priority is facing away. So then it implies that the configuration at position 2 is going to be R instead of S. The The one at position 3, if we try to do the same, will be 3s. The one at position 4, if we try to do the same, will be 4r, and the one at position 5 will be 5r. So the trick here that you can employ is, if you draw the compound properly with the carbonyl being at the top, and you label the OHs exactly where they're supposed to be for the specific sugar, then if OH is on the right, then that is going to be an R configuration. If OH is on the left, then that is going to be an S configuration. Another designation that we use is called the plus or the minus, and this depends on whether the molecule rotates a plane polarized light in the clockwise direction or in the counterclockwise direction. When it does it in the clockwise, we call that dextrorotatory. When it does it in the counterclockwise, we call that levorotatory. So we can either use these letters D or L, but commonly we use plus or minus because this italicized D and L kind of cause a confusion with another D and L that we are going to learn later. So we are going to say that up to now there are two methods by which we can designate the configurations. We can use R or S, and we can also use plus or minus. Now keep in mind the plus and minus have nothing to do with the R or S. So the R or S is simply to determine the configuration with respect to the priorities according to the Kern-Ingold rules. So with the D and the L designation, here we only look at the bottom stereocenter. So the bottom stereocenter, in this case, we have 1, 2, 3, 4, 5, and 6. Only carbon number 2, 3, 4, and 5 have stereocenters because they have different substituents on the carbon. So the bottom stereocenter is the carbon number 5. Now we look at the bottom stereocenter and determine whether the OH is on the right or on the left. If OH is on the right, we call that a D sugar. If OH is on the left, we call that an L sugar. So most of the naturally existing sugars have OH on the right. So most of the naturally existing sugars are D sugars. But if you look at these two again, you will notice that they are actually enantiomers, so mirror image of each other. So the D is simply a mirror image of the L. These configuration strategies can help us to classify sugars and to develop a family tree, either for the aldoses or the ketoses. Now, starting from one with only one stereocenter, which means that we can have either the L or the D, it implies that this represents two sugars. Now, when we have these two stereocenters, again, we can stagger the OHs, and with two stereocenters, we can end up having 4 sugars. So we're only showing the D, and then there's the mirror image, which is the L. So in the L, the OH here is going to be on the left. Again, the other one, the OH here is going to be on the left. So kind of the exact mirror image of each of them. When we have 3 stereo centers, we can be able to stagger these OHs and end up with 8 different sugars. So the ones we are showing are only the D, and then their mirror images is going to be the L configuration. So we end up with a total of 8 sugars, and then finally here at the bottom we end up with 16. So taking the total, what we are showing here represents a total of 30 D, 30 aldoses, both the D and the L. So there's a total of 30 sugar molecules that have the functional groups, the aldehyde. We can do the same for ketoses, which I have demonstrated to you guys in the lecture notes. So you can refer to that and let me know if you have any questions. Another thing I want us to look at is how the sugars can be able to interconvert. Now, if we start from D-glucose, in the presence of a base, this sugar can undergo tautomerism. So it transforms from the carbonyl into an enol. Then the enol later on transforms back into the sugar. When it does that, the stereochemistry at position 2, the one with the red labeled hydroxyl group, the stereochemistry at that position ends up forming mixtures. So we end up with 50% where the OH is on the left and 50% where it is on the right. So when that happens, we are going to form epimers. So epimers are compounds in which the only difference is the stereochemistry at one position. So like here, the stereochemistry at position 2. The stereochemistry at position 2 differs just with the arrangement of the OHs. So we call those ones epimers. Now this would happen whether you have a 6-membered ring or a 5-membered ring. For example, fructose usually prefers to exist as a 5-membered, though there's an equilibrium between the 5 and the 6-membered ring. And then in the presence of a base, this compound would actually be able also to transform into a linear configuration. So when there's a base, it undergoes tautomerism and then gets back to the sugar and it forms these epimers. The epimers can then be oxidized, and when we oxidize them, we end up forming, like in this case, we form a gluconic acid. And then we also form mannonic acid.